Hello, welcome to session number 5 in the series System Design. My name is Anurag Nigam, and we are talking about system simulation in System View. And what we had started was analysis of a RS system in Spectrosys, and we had constructed a transmitter, and in the last session, and it looked like that. Okay, and we were using 11 megahertz as the input, and we were up converting it to 3.5 gigahertz band, followed by amplification and then filtering, and this was the output. And if we look at the results at the output node, sorry, this is cascaded gain output node, we were putting out 20 dBm roughly, with minus 50 in here, or now in this case minus 45. We are putting out 24 dBm in each tone, so that is equivalent to 27 dBm out, right? So that is the kind of power we are putting out. Now we were going to construct a channel over here and then look at the receiver. So that's the plan for discussion. So at present, let's discuss something. So first thing is, when a signal goes through the wireless medium, for example, it goes through something called path loss, and one has to be very clear what this path loss is and why, and its dependence on the wavelength, right? Second thing is it's going to go through absorption, and third thing is going to be, if it's a directional antenna on both transmit and receive side, then it is going to see beam mismatch losses, right? And apart from that, it is going to pick up some noise in the channel. Okay, so we are going to look at this one by one. So first of all, what's a path loss? Let's say we have a point source of radiation, then it's going to equally radiate. For an isotropic case, it is going to equally radiate, and if it equally radiates, then the energy, which is, let's say power is Pt, and if I look at a distance of d, or let's say r for example, then the power density over here is going to be Pt times of Pt divided by 4 pi r square. And if there is a directionality to it in form of antenna gain, that will be Gt, right? And then Ae is the aperture of the receiving antenna, so this is going to be the receive power, right? So path loss is because of the energy diverging out in the space. And then in an isotropic case, the antenna gain is going to be 1. So in that case, that is the worst case for this transmission. In case the transmitter has a gain of Gt, and receiver has a antenna has a gain of again Gr, then the situation is much better. So now let's see what is this antenna aperture. Antenna aperture is related to antenna gain by this relationship, right? And this will be the receiving antenna gain. So I can write the aperture to be Gr times of lambda square divided by 4 pi, and that if I substitute in the above equation, I'll have PR will be equal to PT GT GR, and then there is going to be lambda square divided by 4 pi r whole square. Okay, and if I look at the loss, it will be PR by PT, which will be equal to okay, so if it's a, hang on a second, PT by PR, right? So that would be the loss. Okay, so pt divided by pr, in that case it will be equal to 4 pi r square whole square divided by gt gr lambda square. Now if I express this in dB, so this is a path loss in dB, that will be equal to 10 log 10 of this number, which is 4 pi r square whole square divided by lambda square minus the gt in dB minus gr in dB. So this is the nature of the loss which you are going to see when the signal goes through the wireless medium. Now notice that lambda square is in the denominator, which means that you will have to put out more power to overcome the path loss at higher frequencies. So if you are trying to transmit at 60 gigahertz versus 6 gigahertz, your loss would be almost 100 times more, because it is a lambda square, right? So I hope you understand why transmitting at high frequencies is an issue. You will have to generate power at high frequency. You have to generate higher power to meet the same distance, and that's why most of the mobile phones in 5G are still under 6 gigahertz or sub 6 gigahertz. When it comes to Ka band and when it comes to V band, this scenario is okay for indoor communication, short distance communication, but for long distance communication, Ka band and Q band are not good unless you are doing the line of sight inter-satellite links, or satellite communication. In that case, you can have a very high directivity antenna to compensate for the path loss, right? So there it might work, but for your consumer electronics, I see this is far from reality to be using 5G and Ka band for long distance communication. It's not going to be like sub 6 gigahertz communication. So having said that, let's see what are the other factors. The other factors you can see is the absorption. Now absorption mostly is in two bands. One is the water absorption in 2022 gigahertz band, and then oxygen absorption band is around 66 gigahertz, right? Besides that, I don't see a lot of absorption issues here. There may be dispersion in rainy environment where there is a drizzle or something, but then that's a short time phenomena, right? Other than that, I don't think that there are more sources of absorption. Now coming to the third one, which is the beam mismatch. So as we have discussed, the antenna has to be directional to have large GT end. So let's say that this is a transmitting side and this is the receiving side, right? So this beam mismatch loss would be there if it is a high redirectional antennas, and at that point this pointing, or this becomes important, right? So all these things are there. That's why we have antenna subsystem in higher frequency systems, which can handle this beam alignment. Okay, so that's one scenario. The other issues are, for example, in multipath communication, where there are multiple paths between the transmitter and receiver. Then in that case, the signals arriving at receiver are in different phases, and as they are modulating the carrier, the carrier may arrive at different phases, and if it arrives totally out of phase, then it will be a destructive interference at the receiver, and that would be called fading. And the fading is the okay. So what can happen is, in the multipath case you can have fading, And then it is fading is also it is not always there, it changes with time, right? And especially when the channel is not stationary, right? And stationary, I mean that the channel characteristics change over time. Now if they don't change over time, it's a stationary channel. If they do, then it's a non-stationary channel, right? So those issues will come in. And second, if the transmit and receiver are mobile, not fixed point, then this scenario is more common. So multipath fading and channel distortions would come in, right? So that's another thing. As far as the noise is concerned, thermal noise is always there, and that noise floor is minus 174 dBm per hertz at room temperature, and this is mostly your Boltzmann constant multiplied by the temperature divided by the bandwidth, right? Multiplied by bandwidth or then divided by bandwidth. So basically it is Boltzmann constant into temperature, right? So that's a thermal noise. Besides that, there may be other noise pickups, so we can model that in our equations, right, or in our schematic. So let's get started with what we are going to do with this, and we are going to analyze the transmitter receiver in channel. So to model the channel, first I'm going to add some parameters. So add a tab, and in that case say add parameters, and in that case I am going to add distance d. So this would be a distance, and distance in meters, right? So units you have to be clear. Let's say 30,000 meters is 30 kilometers, right? That's the default value. And length meters, and I'll tune it. Next is I can add frequency to it, because path loss is frequency dependent, right? So I'm going to put here frequency fc, and here it is frequency. So just a second, bear with me. So that's a frequency in gigahertz. So right now I'm going to put 3.5 gigahertz. Okay, and that also is tunable. Then I'm going to add the antenna gain, which is in dBi. So basically I'm going to not declare the units, but this is a transmit antenna gain. And I'll put this as 10. I'll not put the units. Then I have the receive antenna gain, GR. Just bear with me. Right, and that also I put as 10 dB, and all these numbers I'm going to put as positive integers, though there is no restriction on a floating point number, but I'm going to do that. Now I have also inserted equation tab, and here I'm going to define path loss. So first I'm going to define lambda. Okay, so lambda is going to be C over F. So C is 388 over FC. So that gives me lambda. And then the path loss, P loss, would be equal to 10 times of log 10 of some number, which is going to be something, which is going to be 4 into pi into r divided by lambda, right? And this entire thing is square. So it will be raised to, so in MATLAB it's this raised to 2. So this is going to be path loss. Now another thing is, to this path loss I'm going to include the gain, which is going to be GT minus GR. Okay, So that's the kind of path loss I'm going to see. And if I just run this equation, right click and run, under design variables, I see P loss. What happened to P loss? Okay, equation R. Okay, in this case, this is not R, this is going to be D. Okay, so that's fine. So let's run this again. Okay. So again, lambda. Okay, so we have path loss as 112 dB. Okay, so this is over a distance of 30 kilometers, right? So fine, this part is clear. So the way I'm going to model is, I'll go to my bench, which is, where is it? Okay, this is this. So I'll go to my bench, and here I am going to put in the loss. So in that case, I'll put it as a attenuation, ATT. So that's the attenuator. And here I'm going to specify the loss as P loss, right? So that shows up at 112.88. So that's there. And one more thing which I am going to do is I'm going to subtract 3 from it, because I'm going to add something over here. So let me show you what I'm going to add. I'm going to add noise. So I will go to splitter. Okay, look for splitter. So a two-way splitter with 0 degrees. And then I am going to mirror this out. And that splitter I'm going to keep here. Right? So here I can inject noise. And I am not going to touch this 3 dB, because the way this splitter is implemented, it says it's going to combine the equal amount of power. So basically it's a 3 dB addition. So that's why I'm going to subtract out 3 dB from here. So I'll go to equations, and I will insert here -3. So I'm going to say run equations. So that's done. Okay, and here I'm going to put a noise. So I will go to multi source, and I'll put a multi source here, and here I'll add white noise, and I will go from 1 megahertz to, let's say, 10 gigahertz, right? And the noise I'm going to add is going to be 10 dB above the thermal floor, which is going to be 165 or 164, right? And I'm going to put here 100 points or maybe 1000 points. That's okay. So I have put in a white noise here, which I'm going to couple in here. So that portion is done. So now what has happened is, I have modeled a channel here. Okay, so this is basically image reject filter, and then there is a channel here. Now I wanted to talk to you about this image reject filter. What is it for? So what happens, so just one second. Image reject filter usually is beneficial in case of heterodyne receiver where there is a IF frequency. So let's put down what does it look like. So let's say we have a frequency which is a FRF, and then I do a low side injection which is LO, right? And this gap of frequency is called the IF frequency. This is for a heterodyne case, right? Now let's say I put in a filter here which is doing something like this. So this is an elliptic kind of a filter, right? okay, which is doing this. So I put on a filter like this here, right? So now what's going to happen is at the output, I'm going to get sum and difference frequencies, right? So on the left side, which is the distance of again IF, I have an image frequency, IF image, right? So this is a F image frequency here. Okay, so F image will also appear at IF frequency once you mix it. Allo with F image will also. So this image, because this is going to see all the rejection of the filter, so this thing is going to be rejected. So that's why it is called the image reject filter. Another thing which this does is all the noise in here, okay, will also show up here, right? So basically noise also, it's going to get rid of that noise also, which will come in band. Now in case of direct conversion, okay, the IF is 0. So you are mixing RF with LO, which is same as the RF frequency, and the band, the bass band, basically the positive and negative frequency are going to fold over like this, right? And there are things which are there to consider here is that in heterodyne, the closest frequency between LO and RF is a half IF, somewhere half IF. And why half IF is important is the following. If you mix twice of LO plus half IF with twice of LO, you are going to get the difference to be IF. So half IF will appear at the IF frequency. Now this problem is severe with half IF. With 1/3 IF, it also exists, but it is not that severe because 1/3 IF is more close to LO, much far away from RF, and the filter skirts are going to take care of that, right? So the worst scenario is for the half IF situation, and that is why the SOI of a receiver is more important than the TOI. While in case of what you call direct conversion, okay, the linearity becomes more stringent, requirement on linearity, because it's not only the even order mixings which are going to appear in the baseband, but also the odd order mixing will come into basebands, right? So in that case, that's a much severe scenario, and the image reject filter cannot do anything about it when it comes to noise coming from the bands. So the noise condition is much worse in case of a direct conversion, because your filtering will not be able to get rid of that, right? So I hope you understand the difference between the two. So what we are going to see is what is the situation in case of a direct conversion. Okay, so going back, I have done this, and if I look at the output, okay, so let me just run this again. The loss is 109, right? And then this is there, and 3 dB is there. Okay, and edit. Okay, that's the white noise. So why is it not simulating? Let's see if there is an error here. Okay, let's see what has happened here in terms of power. Okay, so now you can see in terms of power, where are we? Okay, so over here, this is minus 88 and this is 96. So basically I'm looking at a worst case scenario where I am transmitting around 27 dBm of power in two tones, and the distance is 30 kilometers. So the distance is 30. Okay, so fine. So we are looking at our spectrum here, and we hardly have okay. So sorry for the distraction. Okay, so we have minus 8 dB of signal to noise ratio at the antenna of the receiver when it goes through the channel, right? And then we have also added some noise to it. That's why we have that signal to noise ratio. Now over here, first thing I'm going to see is something similar to this BPF. So control C, control V. So I'm going to see that BPF over here. So that is the image reject filter. And then I'm going to see a LNA, which is going to be similar to this PA, but its noise figure is going to be much smaller. So the noise figure, so let's say the gain I put here is roughly 20, a typical gain numbers. Noise figure is of the order of 2.2 dB, and let's say it compresses at minus 10. So that will bring in plus 10 as 1 dB compression, and the saturation power will be at 4 dB to 5 dB over that, and TOI would be 12 dB above that, so that will be 22, and then another 12 dB will be 34. That will be the SOI. Okay, so that will be this scenario. So we have here the LNA. Next is, so let's see what happens to the curves here. Okay, of course, you know, this is the worst case scenario. So this power is 68, minus 68, and this power is 75.7, 76. 68 to 76 is again 8 dB. So signal to noise ratio is still 8 dB in my band, right? Now I am going to down convert this to 11. So I will go to do a direct conversion. So here I'm going to put in a mixer here. So I'm going to copy the same mixer, control C, control V. Okay, and this frequency I will put as a variable frequency, and I will call this as FC. So it's 3.5 gigahertz, doesn't change. And here is again the same frequency FC, right? So I can just copy this block over here, right? Okay. So let's look at some of the numbers here. So what am I getting here? Under compression, I'm going to get 10 out of it, right? So this mixer should be able to handle 10, right? So it has a conversion gain of 10. So basically you want this mixer to be very linear, right? So you will compromise all your conversion gain for that. So let's say conversion gain is roughly 2, right, or 2.5 dB. I have compromised conversion gain for linearity, right? And noise figure is as bad, but then the compression, you can see if I put out 10, so the output will be, so 10 is the output from the LNA, worst case, on the higher side, 10 is the output. So the mixer is going to be, all this is referred to the input, right? So this would be around 10, and from the previous stage, and then IP set is roughly going to be 15, and this is going to be 22, or let's say in this case 25. Let's make this 12 and a half, or 12, some margin, right? So let's put 12. So this one is going to be 12 dB above that, so it will be 24, and 12 dB our risk will be 36. So this is how the mixer is going to be behaving, and this is going to be a difference frequency. Okay, so this is a difference frequency. So now we are back to 11 megahertz, right? And if I was to simulate this, so let's see what is the LO power 0, right? Yeah. So if I was to simulate this, okay, no warnings, no errors. Let's look at this curve. Oh. Okay, so we are at a different place now. Okay, we will not be looking at 3 point something. Rather, we will be looking at 11. So we are over here now, because we have down converted. Okay, so here this is 11. So both plus and minus 11 have folded back to the frequency of interest, right? And the signal and the noise is minus 70, and signal is minus 62. So it's still 8 dB here. Worst case signal to noise ratio is still 8 dB here, right? So with that, the power is minus 62. Okay, so now this is beyond the mixer. Now here, if you want, you can get rid of all other components by putting an LPF. So I am going to add here a design, and I will call this as a LPF dash. Okay, and here I am going to put in LPF Chebyshev maybe, and here I am going to specify insertion loss of 0.1 dB, order as 5, and the ripple as 0.1, f pass at 30 megahertz, for example, because now we are sitting at baseband. A pass as let's say 40 dB as attenuation, and A max is 100. Okay, so we are done with it. Let's look at its characteristics. So let's put the input port, and let's put the output port. Okay, so we are done with this. Let's do a analysis which is linear, and this time it refers to LPF, and I am looking at its characteristics from 1e minus 3, which is kilohertz, to something like 100 megahertz, and I'll put 501 points here. Right, and once this analysis is done, I'll go here, add a graph, and look at the result in the general linear LPF design, right? Under that, I'll look at S21, S11, and S22, and say OK. So this is the characteristics of the low pass filter, right? And this will well, accommodate 11 megahertz. So the entire baseband would be here, right? Okay, so this portion is done. So I'm going to take this LPF, Control C, and I'm going to put this over here. Control V. Okay, so now we have LPF also in the picture here. And if I look at the characteristics, they are hardly going to change because LPF doesn't do anything. It's a 0.1 dB. Right. So, but it cuts out all other components. You can see that it cuts out all other components. So you are just having the baseband over here. Rest is all cut out here, right? You can see all this high frequency components are gone. So our focus is on baseband here, right? So, and this is the edge of our baseband, 11 megahertz. Okay, so now I have given you some idea of how to construct this receive channel. But here you see that the gain is 20. I want something like let's see, control a gain of 60 dB on this. So I am going to put in 40 more dB here. Okay, so now this is 20, this is 22 and a half, right? And 22 and a half and 12 and a half is where it is compressing. So this one has a gain of, let's say, 40, which can be 2 or 3 stages. Okay, and then the noise figure is really bad. This is baseband amplifier, right? And OIP, if I was to add 12 and a half plus 40, okay, 52 and a half. So basically this can handle very large voltages, right? So what should I put here? 12 and a half plus 40, 52. Okay, let's put here 52. And that would be 55. And that would be 64. And that will be roughly 74. Okay, so these are all the analog blocks, right? This is not a RF block. So you can have large voltage ranges here. So anyways, the way to handle is just put in numbers like this. Okay, so now if I was to simulate this again, okay, so everything has gone up, doesn't matter. So now the power is at minus 23 dBm. Okay, now usually if you look at the specs of ADCs, you will get a certain dynamic range. Okay, and you have to look at the distances, the highest distance and the shortest distance, to look at what should be the dynamic range in which you should be operating. And this would result in maybe this variable gain IF stage. So the IF stage which I have added can be a variable gain. So this can be a variable gain. Okay, and again, if you are looking at SFDR of this entire receiver, then a portion of this gain may come from a variable gain LNA, right? So that will increase the SFDR. Okay, anyways, so here let's look at the signal to noise ratio. Okay, the signal is minus 23 and the noise is minus 30. Minus 23 minus 30.2, so it is around 6.8 dB or something like that. Okay, so still at 30 kilometers, if I choose a detector with a signal to noise ratio of 8 dB, worst case, it will still detect a source at 30 kilometers. Now let's go ahead and put distance on a tune. So I will put what you call a slider, and here I am going to distance. Okay, I'm going to choose distance, and here I am going to hide the prefix and say minimum is 10 meters, maximum is 60,000 or 60 kilometers, right? And here I'm going to put 10 ticks and snap to integer value and say okay. Okay, so now I will disable these two. Okay, first of all, let me compute all of them. Okay, now I'm going to enable only system simulation. Okay, so basically only this one is enabled, and this one I have put on automatic recalculation, right? Now, if I was to look at this now, let's say I go 10 meters and look at this signal to noise ratio. Okay, and so let's put this at 10 meters. Okay, so that's at 10 meters. Okay, so at 10 meters, uh, I am putting out 45.253, and this much power basically would compress lots of stages in between, but I'm just putting the minimum distance, right? And so I can vary this and see. Now what is this? This is the noise. Okay, so the noise is like -3 or -4 here. So signal to noise ratio at the end of the chain is very good, so demodulation will be good, but then you should also look at the cascaded gain. So in that case, let me put the gain chart here, which I did last time. Okay. Okay. Now keep in mind which is what stage. Okay, so you are here and we are looking at a receiver, right? So here this is a PA. Okay, so let me just expand this out. Okay, so this is a PA. So gain over here is here is 39.6 and here it is 69.2. So the gain was 30, right? So 39.6, it should be 69.6, so it is a 0.4 dB compressed here. So the PA is 0.4 dB compressed here when it is putting out 27 dBm, right, in two tones. And then this one basically is showing you gain. Yeah, so I'm putting high power. So here, this is what a receiver is receiving, right? After putting in noise and everything, we are over here. So this is what a LNA is seeing. Okay, so here it is 25.6 and here it is 45.4. So LNA is 0.2 dB compressed here, right? And then mixer over here is 45.4 and this is 47.7. Okay, so again the mixer is 2 dB compressed here, 0.2 dB compressed here, right? And similarly this final amplifier, which is 47 dB, 47.3, and this one is 87.2, right? So this is 40, so this is again 0.2 dB compressed. Okay, so everything is going to go through compression if you are hitting on the high side. Now this is not what the power levels are going to be, because 45 is too high. 45 is too high. It will just saturate out from rail to rail. So that's not what is going to happen. So let's go ahead and put realistic distance here. Let's say 100 meters. Okay, and let's look at these numbers. Why is it not doing it? Hang on. Let's reduce the number of points in the noise. Let's close this, not this one. this one. Let's reduce the number of points in the source. Multi-tone case. Edit. Because this is flat anyways. Okay. And so it should auto calculate. Hang on. Okay. Minus 23, minus 30. So we are at 30 kilometers here, right? So we are at 30 kilometers. And if I go above that, so here it is minus 18 and minus 30. So this is around 12 dB signal to noise ratio, and we are at 15 kilometers, 16 kilometers roughly. And now we are at 7.8 kilometers, right? So let's see what's happening here. Okay, at 7.8 kilometers, I'm at minus 12 dBm, and this one is minus 30, so around 18 dB signal to noise ratio. So let's go down to, now we are at 1.5 kilometers, and at 1.5 kilometers, okay, this power level has gone up to 1.8 dBm, right? And this one is minus 30, so we are well above the signal to noise ratio of the detector. But here it is minus 1. It is around 1.8 dBm. So basically, if I go further down to 100 meters, I am at 25 dBm. So of course 100 meters means that this is going to saturate the receiver. So now I'm at 270 meters, 2 kilometers already. So let's see if I can get 500 meters. Okay, so I can type that over here if that's the issue. I can put here 500, say yes. So that's a half a kilometer, and at half a kilometer I'm putting out 11 dBm. Okay, so at half a kilometer my detector is seeing 11 dBm of power, which is going to be a voltage swing of around more than 1 volt on the ADC. So you understand, you have to have this in the range, dynamic range of the ADC. So at this point, which is 500 meters, my receiver is going to have a full swing across the supply, right? So beyond this, the receiver is going to saturate out. So I cannot, if I have to constrict beyond 500 meters, I will have to put a variable gain on this stage. So there is always a power control loop, okay, which is basically controlling the power which is hitting the receiver. So it will either vary this gain of the LNA, or it will vary the gain of the IF stage, and then you can go even closer than 10 meters, right? So that's how the higher end is achieved, by putting a variable gain. Now as far as the lower side, the detector, let's say I have chosen to be 3 dB signal, worst case signal to noise ratio. So let's see what is the kilometer range I go to where I hit 3 dB. So right now I'm at 40 kilometers. So at 40 kilometers, didn't update. So let's accept that. Okay, at 40 kilometers, I am looking at power of minus 24, minus 30, and minus 24 and minus 30, minus 31, minus 25. So it's still 6 dB. So I can go ahead and increase the distance further. So right now I'm at 50 kilometers, right? So at 50 kilometers, let's see what is the signal to noise ratio at the detector. So at the detector, I can put an axis here. Y-axis, I am going to put 0. X-axis, I am going to put, let's see, minus 30 to 0. Minus 30 or minus 20 to 0. Okay, of course 20 was out of range. Minus 28. So I just see the top of it. So minus 40 to 0. Okay. So here I see minus 26 and the noise is minus 31. So hardly 4 dB here. So at 50 kilometers, I'm hitting a signal to noise ratio at the detector to be 4 dB, which is well within the range of, a detector signal to noise ratio. So you can see in this bench, I have the transmitter, I have the channel with the noise, and I have the receiver side, right, with the down conversion and all the filtering. Now in this we can look at the cascaded gain, but the cascade gain has cascaded noise figure, but the cascaded noise figure chart will not have a meaning because it will be characterized around a frequency, right? And we are going through a conversion, a down conversion here and up conversion on the left side. So the numbers will not make sense because they are around wrong frequency. So the better chart to see in this case would be, if I go to graph, I can add here, sorry, not graph, cancel this. I go here, sorry, I go here and add graph and say carrier to noise ratio. Okay, so now when I hit here, this is minus 5. Okay, so even this will not make sense. This will not make sense because the frequency at which it is characterizing is changed over here. So you are drastically going to drop. So this is 2 dB here, and then suddenly it will become a negative number. So this would not make sense because you are not at 3.6 gigahertz where you are seeing this characterization. So mixers are the ones which are going to change the frequencies, and then this meaning of cascaded noise figure or signal to noise ratio will not make sense because you are changing across the chart the frequency. So that will not make sense. So rather the best thing to see in this case would be the power tones, and you can compute the signal to noise ratio by subtracting these two numbers, minus 26.4 and minus 30.6. So that is around 4.2 dB of signal to noise ratio at the detector, worst case. So at that point is the limiting case where I have, just one second. Okay, sorry for the disturbance. Okay, so we have hit here 50 kilometers, and at 50 kilometers we are barely meeting signal to noise ratio at the detector, okay, which is around 4 dB, right, for which we have designed. So this is the lowest limit, and the sensitivity numbers would be at the input of the receiver. So if I go here to this chart and plot the same power curve at the input of the receiver, which is over here, right? Which is over here. No, over here, sorry. So at this point, if I was to plot the power graph, okay, and if I go here, look at these two numbers. So this is minus 91 and minus 91. So this is going to be 87. Okay. So this is the minimum power which receiver is going to detect, right? I would like to keep this number at around, okay, this is minus 96, right? So minus 96. So hang on a second. Okay, minus 87. So I would like this receiver to be even responding to 106 or something like that. Then we have to figure out, what should be the gains and what should be the cascaded noise figure. Okay, to be able to detect it 106. Okay, so one way would be to work with the noise figures, right? One way to work with the noise figures to bring the sensitivity numbers down, right? And the other way is to work with the gains. Okay, so if you go to the Ferris formula to can calculate cascaded noise figures, so you will know that what we have to work on, right? Okay, okay, so now this is a receiver in conjunction with a transmitter, right? Now the transmitter power is held to be constant, which is the highest power, and the transmitter is transmitting the highest power, and the receiver is basically receiving the lowest amount of power as minus 86 minus 87 dBm. And to improve this, one more way would be to have higher directionality antennas. So we have to change the antenna gains. Okay, so that will also come into picture. If you do that, then this number, sensitivity numbers will improve if the gain of the antennas are increased, right? So then this can go way down this can go way down minus 106. So you see that the design of a communication system is not done, separately. It should be done in unison. The channel should be there, the transmitter and receiver, and system view provides you a way to do that, right? Okay, so you can play around with lots of things. So for example, you can bring down the noise. Well, you are looking at worst case scenario. For example, I'm adding 10 dB noise above the thermal floor. So had I brought this down, for example, I can put another tuner and bring this down to the thermal noise case minus 174. In that case, let's look at not this one. Node 7. What is node 7? Yeah, here. This is the receiver, right? So here it's minus 93, and let's look at the output node. The output node now sits at minus 27, and the noise is at minus 36, which is basically 6 plus 3, 9. So right now it's 9 dB, right? So I can bring the power down again. So just see what the noise is going to do in the channel to the sensitivity of the receiver. So if you bring down noise, you can even increase this distance to go to, let's say, 60 kilometers. And in that case, sorry, no, 2. In that case, I'm at minus 28, minus 29, and this is minus 36, still 7 dB. So I can even go and reduce the power further, right? I can have a longer distance here. So you can see what this noise in the channel going to do, right? And in this case, let's look at what is happening at node 7, which is the input of the LNA. It is at minus 94, and this is at minus 90. Yeah, so this is at minus 94, or sum of the two nodes is going to be 93, minus 93, right? Hang on. minus 91, and this is 98, so 7 dBm. 7 dB is the signal noise ratio. So in this change you can vary a lot of things. You can look at signal noise ratio at any point, and then you can look at your compression characteristics of various stages, right, using cascaded gain like this across the channel, right. And then you can also see whether you are in the right range of the detector, right. So that means that if there is ADC, you have to be in the range of that ADC, and then you can put a variable gain in here to meet the right range of ADC, or rather the right distances to which the receiver is going to respond, right. So I am going to stop here, right. I have tried to explain you the transmitter part, the channel, and the receiver part. Now you can make it more complicated by different architectures of a receiver, and you can work from there, right. Thanks a lot. Thank you very much.